Hello out there again. I'm Dr. Bettina Heinz, ready to give you another exciting lesson in chemistry. Today we have equations of chemical reactions. Very important because so much is based on the chemical equation. So we have to say that in the chemical equations, reactants produce products. So we have things on one side of the chemical reaction and things on the other side of the chemical reaction, so to speak. And we have a shorthand way of determining this with symbols, the formulas, the arrow that shows us what products are yielded. So we will learn about writing and balancing equations, what the subscripts and the coefficients mean, word equations, the skeletal or unbalanced equation. And remember that when we have a chemical change, the atoms just rearrange themselves. So old bonds are broken and new bonds are formed. So we have the conservation law of mass to consider. Then also we will touch a little bit upon the law of mass action, equilibrium, kinetics, meaning how fast a reaction proceeds, a little intro on the rate laws, and Le Chatelier's principle. Then we will also show a video on a certain type of reaction which we call combustion, and that will produce oxygen, but I'll tell you more about that later. These slides are just quickly for you because I'm repeating them. We see here magnesium and oxygen produce magnesium oxide. That's a chemical change, and we have here also shown the shorthand way of writing the chemical reaction. And we have also a balancing act fulfilled. That means that no atoms are lost or produced. The combustion of magnesium, this is the method. We've learned about this before, so I'll just go through it quickly. It's an exothermic reaction that is typical for a combustion reaction. A lot of energy is produced, and in the end we have a new compound which is called magnesium oxide, a white powdery substance, very different from the original magnesium metal ribbon that we used. And we have a side product also because chemical reactions are not always so straightforward. We have a lot of side reactions. So a byproduct here is magnesium nitride, which can, however, be destroyed by water to produce magnesium hydroxide and ammonia, and the magnesium hydroxide is returned back to magnesium oxide. So let's look at the chemical equation once again. Remember, we have reactants yield products. That's very important. And notice the difference here between the numbers. We have the coefficients and the subscripts. The subscripts must never be changed because they indicate the type of chemical we're dealing with. So you can't do any identity change of a chemical substance. They wouldn't appreciate that. So they have their pride in their own identity. What we can do, though, in order to balance things out, is use the so-called coefficients. And the coefficients are just numbers that multiply whatever is behind them in the formula. So if I say 2 magnesium oxide here, that means we have 2 magnesium atoms and 2 oxygen atoms, which corresponds to the left side with 2 magnesium atoms and already 2 oxygen atoms in the diatomic molecule. The coefficients tell you a lot about the particle ratio, but also the molar ratio. Now we come to something very interesting, the so-called law of mass action by Cato Maximilian Guldberg and Peter Waage. They are both Norwegian, and they studied forward and reverse reactions or backward reactions, and were the first to formulate the so-called law of mass action. That means when we look at a molecular reaction, for instance, nitrogen dioxide producing dinitrogen tetroxide, this reaction can go back and forth. That means the forward reaction has a certain regulation or certain conditions, certain properties of speed or heat production, energy change, etc. And the other reaction has its own properties in reacting, for instance, as far as velocity goes or thermal exchange goes, etc. So we have here the equilibrium between the production of the products, and we have to use the square or the power of 2 of this concentration of nitrogen dioxide divided by the original reactant. So that would be the reaction leading to the individual small molecules or the breakup molecules, and the reverse reaction would have to be formulated in the opposite way, where we exchange the numerator with denominator. These two gentlemen stated that if we maintain that for a given chemical process 2 opposing forces are in effect, one which strives to form new substances and one which strives to restore the original compounds from the new, it is enlightening that when in the chemical process these forces become equally large, the system is in equilibrium. That means forward reaction is balanced out by the reverse reaction. And every reaction has its own equilibrium constant. This law of mass action is formulated here again. We have the reaction quotient, which does not necessarily mean that we are in equilibrium, but K is always the equilibrium constant, and Q would be the reaction quotient, and when Q becomes K, the reaction is in equilibrium. So any chemical change proceeds until an equilibrium is reached. This is all very important and will be more discussed in higher level chemistry classes. But I certainly want to introduce you into these interesting subjects. An equilibrium is usually dynamic in chemistry. It can be an equilibrium between 2 physical states, but it can also be an equilibrium between reactants and products. We can sort of compare this to a library. At opening hours, there is a balance between people coming in and a balance between people going out of the library. So that is what we would call a dynamic equilibrium. We can also relate the chemical equation to how fast it proceeds, and that is what we refer to as kinetics, or the chemical velocities of how the reaction proceeds within time. For molecular reactions, we have an energy profile diagram. That means if this is the energy level of the reactants and the other side the products, we have a mountain to climb. That means it's not that easy to get from one state to the other. We have to supersede this energy mountain, so to speak, or hill, and the transition state is on the top. That transition state actually leads to the production of products. We need a certain amount of activation energy. Catalysts are able to lower the activation energy so that things happen faster. The reaction rate in general depends on concentration, how many particles do we have to react, the velocity, that means the temperature. The more energy the particles have, the faster they can, so to speak, supersede the energy hill, and catalysts can lower the energy hill, the activation energy, and therefore you can get over here much faster. It's like flattening a hill. Now, reaction rates and laws are also interesting. We see here again the reaction I just talked about with the dinitrogen tetroxide breaking down, decomposing into nitrogen dioxide, 2 nitrogen dioxide molecules. One is diamagnetic, one is paramagnetic. This you can learn about a little bit later on. One reaction is endothermic, the reverse is exothermic. So we have the back and forth of this reaction. So every reaction we can say is essentially reversible. One can study this mathematically by the so-called rate laws, which have to be determined experimentally. So we have different orders of reaction. For instance, first order, where the concentration of one substance to the power of 1 is only important, or we can have the second order of reaction, which is an exponential influence, and we have the concentration going into the rate law equations in powers of 2s, for instance. This is all discussed in later classes. Now we want to look at balancing a chemical equation. This is so important, and many students have problems in this regard. But I will tell you some nice clear-cut methods. We can balance a chemical equation mathematically. I will go into that later, or just by inspection. And inspection means we just look at the numbers. For instance, we have here combustion of methane producing carbon dioxide and water. Of course, you have to have the skeleton equation. The formulas have to be all correct. And then you can sort of seesaw back and forth and see what kind of coefficients you need. That's why I always do an inventory if I'm not careful when just doing it out of my head. When you're learning, it's good to do an inventory first. So on the left side, we have 1 carbon. On the right side, we have 1 carbon. So that would be balanced. So we compare and change. Hydrogen's atoms are 4 on the left and only 2 on the right. So that needs to be changed. And oxygen has 3 on the right side and 2 on the left side. So this equation is not balanced at all. So I start with 1. Let me see. I'll double the water. So when I put a 2 up here, that means the whole internal part has to be doubled. So 2 times 2, coefficient times subscript, essentially. Remember, the ones we don't write. So 2 times 2 is 4 hydrogens. Okay, we have that here now. And 2 oxygens, plus the 2 that we have from the carbon dioxide, gives a total now of 4. Now, in the end, I just change the oxygen itself, the diatomic oxygen molecules, and put a 2 up front. And then you see we have 4 oxygens on the left as well. So everything is balanced. All atoms are accounted for. That is the whole idea of balancing chemical equations. I will give you another example in a minute, but I would like to say a few words about the important concept of Le Chatelier. Chatelier stated essentially that when you put stress on a chemical equation, or the position, you put stress on the position of the chemical equilibrium, then the equation tries to bypass that stress and reestablish the equilibrium. So you go back to home base. That's essentially what he said, and that means you can play around with a chemical equation. You can add products. You can take away the product. That would shift the equilibrium to the right, the position of the equilibrium to the right. You can add temperature. You can remove heat, so to speak. I shouldn't say add temperature. Add heat or remove heat, or pressure, or change the concentration. So you can play with this equilibrium and even utilize it to produce commercially more product. This was used for the Haber-Bosch process, a very important process that led to the formation of ammonia, which is such an important chemical that is used for fertilizer and all kinds of things. So we have nitrogen and hydrogen give you ammonia. Notice that we have 4 volumes of the gases on the left and 2 volumes of the gas on the right, meaning the pressure on the right is much lower than on the left. So we can play around with this, change pressure, temperature, etc., add catalysts, and thus we can influence the position of the equilibrium. Catalysts do not influence the position of the equilibrium, but remember they enhance the rate of the reaction. Now I'd like to give you another example for balancing a chemical reaction or equation. Here we have some pictures of Le Chatelier, who relied on the work of Van 't Hoff a lot, of course. Nobody works in a vacuum. So here we have the complete combustion of butane, and it just shows the same principle that I already showed you before of going back and forth. This is the inspection method. When we have ionic compounds, we do not always have to break things down into individual atoms. We can use the ions as the whole and balance them out as if they were single entities. The mathematical method is the last thing I want to discuss here. And it's actually quite straightforward. We have here our equation, and we put A, B, C, D as unknowns in front of the individual chemicals, and we make equations for each chemical. For instance, 4A based on carbon is equal to 1C, and so forth. And then algebraically, we can find the right coefficients. This not always works for difficult equations, because then you do more mathematics and actual chemical balancing. But we can also do the redox method that I want to show you here. So you balance out the oxidation half reaction, the reduction half reaction, and then you can also balance an equation very well. I would like to show you now a lab video that shows the reaction combustion. But I must point something out to you. I made a little mistake there. It is the decomposition of hydrogen peroxide into water and oxygen, all right, and not hydrogen and oxygen. So please forgive me for this faux pas. Enjoy the video. Well, welcome back to our laboratory again. We will do another interesting experiment today, and that is the combustion reaction with oxygen of various metals and nonmetals. We will produce oxygen by a very simple decomposition reaction, and we will take a 3% hydrogen peroxide solution, let it decompose into hydrogen and oxygen gas with the help of a catalyst. It could do it by itself, but it would take too much time. So a catalyst accelerates the reaction rate. So we will put hydrogen peroxide into an Erlenmeyer flask, and we have already prepared this here, and add some manganese oxide, manganese 4 oxide to be exact. So I will have to replenish this Erlenmeyer flask a little bit with hydrogen peroxide solution. I'm going to wait a little bit for putting the catalyst in there, otherwise I would waste some of the oxygen. Here we have a wide neck bottle filled completely to the rim with water, covered by a little glass square. And here we have a pneumatic trough which has been developed for the downward displacement of water by gas evolution, formation of a gas. So what I have to do is do a little diving process here. Invert the bottle. There's going to be a little air already trapped in here, which is a problem, but it's not really that bad for our experiment. And then I'm going to submerge it so no more air can get in here. And then I'll put that little rubber hose into the bottle, which will then release the oxygen from our reaction vessel, our gas generating setup. So I'll put some more catalyst in here. And notice how instantly the oxygen is being produced. And you notice that the water level is being pushed down by the evolving gas. That's why we call that downward displacement. And we're going to stop and not watch this whole reaction because it would take too much time. We will get back as soon as the whole water is displaced. And then we will do the combustion reaction, because the wide neck bottle will have the oxygen trapped in here, and then with the help of a deflagrating spoon such as this, we will test our metal or non-metal, submerge it into the oxygen quickly and see what happens. So we'll get back to you shortly. Well, now we are back to our second part of that experiment, the combustion reactions with oxygen. We prepared our oxygen. We have it trapped here in the bottle, like a bottle imp, and it's ready to do some action. We will start with lithium shots. Lithium is an alkaline metal, very reactive, similar to sodium. So I have to carefully remove some lithium with my forceps and put these shots onto my deflagrating spoon. There's a little mineral oil, of course, attached to it. The reactive metals cannot be preserved by themselves. They have to be soaked into mineral oil, because that way the active metals are protected from air or from oxygen. So what I have to do now is activate the metal in the deflagrating spoon, in the Bunsen burner flame. Get it a little excited. See the little purple vapors? That's already interesting. Lithium burns with a purple flame. And then when I think it's pretty well done, I'll just put it into the bottle. You see that oxygen supports combustion. So the normal flame was heightened, and it's still, you see, pretty active. The glow of the lithium. But the oxygen is consumed now, so there's nothing more to react with. I'm going to leave that spoon for a moment, and we can actually move to the second bottle now and use a little magnesium and see how that reacts with pure oxygen. So with the magnesium, I don't have to activate it. Or maybe, no, I wouldn't. Oh yes, maybe a little bit. Now that was attractive, I thought. So you see how oxygen enhances combustion? It is the one that leads to burning and flames, etc. We have one more bottle left, and we can use a fresh deflagrating spoon and put a little red phosphorus into this spoon. And activate it and see what happens. See, it's activated now. See how it burns much more brightly when it's in contact with oxygen. And in a few minutes, we'll come back and check the pH of the solution of phosphorus with water, phosphorus oxide, or any oxide that was formed with phosphorus with water would produce phosphoric acid or type of phosphoric acid. And lithium would produce with water lithium hydroxide, and magnesium would produce magnesium hydroxide. So we have two bases and an acid. So we'll check it with indicator solution. Yes, we said that we were going to test the solutions that we produced by the combustion products of the metals and nonmetals with oxygen to see whether we have acids or bases formed with indicator solution. Here we have a universal indicator solution which gives a bluish, greenish reaction with bases, yellow for neutral reactions, and red for acidic behavior of our solutions. So I'm going to put some drops in here. We can't guarantee success, but yes, look at here. It's more on the blue side, or purple in this case, but definitely indicating a base. Aha, here also. So remember, metal oxides with water give bases because the metal oxides are basic anhydrides, we could say, and non-metal oxides give the so-called acidic anhydrides. That means when an acidic anhydride comes in contact with water, then we get an acid. So phosphorus oxide could be diphosphorus trioxide or diphosphorus pentoxide, depends how well the phosphorus was oxidized, would either lead to phosphorus or phosphoric acid. This would be magnesium hydroxide, and this would be lithium hydroxide. So the reaction was a success. That means we have the bluish indication for bases and the reddish-orange indication for acids. So that would be the end of this experiment. Thank you and goodbye.